Hi. So now let's move on from sequences to something really cool, which is attention, and which is something that we now use all the time. So we've seen recurrent neural networks, and we know that it comes with this hidden state from the previous time step. It gets the input from the current time step, and then it produces hidden for the current time step, and then this hidden state goes into the next time step. So this hidden then goes takes in the next input sequence, and then it produces the next hidden, and so on. So these inputs are also called as tokens, right? So it's just a vector, and for now let's just think that these inputs, which are vectors, are also called tokens. And we know that in an RNN there is this shared parameters, there is just one set of parameters, but this is in some sense the unrolling of the recurrent neural network model. Now see what is happening. No matter the sequence length, that entire thing gets encoded into this one vector, right? So this is one of the big disadvantages. And we spoke about this when we were talking about recurrent neural networks. And this vector has to capture everything, including the subject, the object, the tense, meaning, nuance, all of that. And it's like summarizing one full movie in just a single word, in just this single thought vector. And something obviously has to give, something has to get lost. And this is one of those problems that we deal with in the attention mechanism. So here, this entire sequence was encoded into this one vector, and then we could probably use this vector to then kind of do the decoding bit, right? So this is the encoder, this is the encoder, and this is the decoder. And the encoder creates one vector, this thought vector, and this thought vector then goes into our decoder in what we used to do previously. As we also discussed, there is this gradient flow problem. So if the largest singular value is greater than 1, we get exploding gradients, or we get vanishing gradients. And RNNs cannot learn dependencies beyond 100 time steps. So you have to split it into chunks of say 100 time steps or less. LSTMs can do slightly better, but still it cannot do like really large context sizes. And then towards, so a lot of people these problems were known, and a lot of people were thinking about how to solve this. And the first time they thought about, using this word attention happens to be this paper called Attention Neural Machine Translation by Jointly Learning to Align and Translate. And this was the first paper that used this word attention. And this is from Bengio's group, and it's by this person. And if you read this paper, you can just search for this. If you read this part, it says in this paper, we conjecture that the use of a fixed length vector is a bottleneck in improving performance of this basic encoder-decoder architecture. What fixed length vector? That thought vector that we were talking about, right? And propose to extend this by allowing a model to automatically soft search for parts of a source sequence that are relevant to predicting the target word without having to form these parts as a hard segment explicitly. What it means is, while doing the decoding for any word, it has the ability to go and kind of loop over all the input embeddings, all these input thought vectors, right? So this is what it could do. At decoding step, it could go and look at all the encoding thought vectors. But this obviously is not very efficient because you have to kind of loop over it. And then, so I highly recommend you watch this video. This is by Karpathy, this was the early days, and he was trying to explain this to Stanford students. And this is where he talks a lot about history. He talks about how all these different fields were disjointed. If you read a paper from NLP, you would hear things like, context-free grammars and so on. If you read a paper from, let's say, speech, you will read about melt spectrograms and whatnot and so on. But then transformers kind of united everything. He also talks about his correspondence with the author and how this thing came about, how he started to kind of, so for example, here he says, in the above approach, the cursors would be too hard to implement in the remaining 5 weeks of my internship, so I tried instead something simpler, 2 cursors moving in the same direction simultaneously and so on. So it's a very interesting lecture. We'll link it in the rabbit hole section, but if you get time to watch it, it's about an hour long and I have seen it multiple times. So now RNN is a chain and information flows step by step. You have your hidden, you get the next time step, you get the next hidden, you get the next input, you get the next hidden, you get the next input, and so on. And with attention, every position can directly access every position, and this is the advantage of using attention. So it's not just the previous time step, it's not just the hidden vector, everything gets to see everything at once. And we went from a line to a complete graph, and all these connections can be computed in parallel, and this is what we will try and understand next. So the question that people asked were, do we still need the loop? So the loop of what the previous people were doing when they thought about attention, and this question is what launched the transformer. So Vaswani et al. At Google said, delete the RNN entirely, right? Only use the attention part. So no recurrence, no sequential processing, just attention. So there is no unrolling, there is no this recurrent relation, nothing. It's very simple because it became just retention. And the result was the transformer, and it changed everything. And in the next video, we'll build this attention mechanism from start.